Testing 1, 2. All right, mic is working. Let's get this down a little bit. All right. Woohoo! I'm live. So, I'm working again on my Ultimate-Tic-Tac-Toe AI bot using the Monte Carlo tree search algorithm. So, I left off yesterday. I was, if I'm recalling, I was about to implement the expand function. And to prep that, I had modified a little bit my MCTS node class by implementing the isTerminal, right, to determine if the game is done. Okay, possible. Then I needed a children's node. I mean a children array. Okay, so let's take a look at our algorithm here from the research paper I'm using. Tree policy, right. So tree policy I've implemented right here. So while within computational budget, oh, that's the overarching UTC search. Okay, tree policy. Okay, while node, V is node here. I don't know why V. Maybe for vector, I don't know. Is non-terminal. So node is not terminal here. Do, all right, if node not fully expanded. So node is fully expanded, but I negate that, not fully expanded. Then return expand node. Expand node. Okay, so that's good. So now we need to implement expand. And that expand returns, it returns a node. Is that what it's supposed to do? Return a node. Which means that tree policy is also supposed to return a node. Right? So tree policy returns a node, yeah. Okay. Basically a children node. Either, okay, I get it. So if the node is not fully expanded, if there are still moves that we haven't explored, then we expand. If they all been explored or expanded, then we choose which one seems to be the best candidate. All right, right on. So let's start by choose an action from untried actions. Cool. That should be easy enough to do. So we've got our node. Do we have action, fully expanded, terminal, state? Okay, so we need access to, where's my node class? Where did I, if I do this, oh, it's right there. I'm blind. So possible actions left to expand is private at the moment. And it's also empty. So I need to populate this. Where do I populate this? In the constructor. So this dot possible actions left to expand is going to equal, and we have worked on a function just for that. Now I've got it as a standalone function, but I might end up making it a method. I'm going to reorganize all of that eventually. I just want to get it to work first. Apply action, get possible actions, which return an array of action. That's exactly what we want. So here it is. So get possible actions left to expand is a call to get possible actions, and I need to pass in the state, so this dot state, there we go. Okay. Do I need access to state? Why do I have it as read only? I must be doing something with it somewhere. Well, there's no harm if I've got it as a read only, I guess. Although, let's say I switch it to private. Did I just introduce? Ah, there we go. This is where we need the state. Could have passed the node, I guess. And then the same thing though. It would have just been a level down, I guess. So let's just keep it as read only. Okay, now this is now set to an array of actions. That's cool. Do that in the constructor. Now we wanted to, oh yeah, okay. So hold on, choose an action. So let's store the action right here. And that action is going to be, we're taking our node and we need to, at random, remove an action from possible actions left to expand. I think I already implemented that function in my previous implementation of the Monte Carlo tree search. This thing is so slow. And what about if I try to do it here? No, it just takes me here. All right, fine. Source code, probably in utils. What do I have here? Now, get random int inclusive, splice random. I need those two. A function that removes and returns a random element from an array. It's precisely what I want. So let's get it. Okay, now I'm going to put this in a separate file because this is getting crazy. Utils. Okay. So splice random. Now, I should probably make this a method here. All right, let's do that. Let's call this choose untried action. How's that? Choose untried action. Returning an action. And this is just going to be a call to slice random. I think it was splice random. Splice random. Oh, I gotta pass in the array. Okay, so this dot possible actions left to expand. And it'll return, so I can just return this straight up. Choose untried action. And this mutates it because it's a splice, and that's fine. That's what we want because we want this to be decreasing as we're trying the different actions until it's eventually empty, which will be triggering the is fully expanded. Okay. So that's good. Back to expand. So this action is equal to node dot choose untried action. Right on. Oops. Okay. Now add a new child to the node. So create a new node, which will be a children of the node that we're passing into expand. So node dot, now I've got a children, I've got a private children array here. I should have a function add children, right? Add children where let's see, how do I want to do this? Do I want to pass in the new node, or do I want to create the new node in here and pass in the state, or how am I going to do this? Let's just look at this again. I need an action, and I need a state for which I have applied the action. That's what I pass into my new node. Okay, I'm gonna create the new node outside of the node class. I'm just gonna give it the new node. So new node or child node. How's that? Child node. Of type mcts node. Don't return anything. All you're really doing is this dot children dot push node. Children node, child node. There we go. Okay. Okay. So cool. So now I need to, in here, node dot add children, or add child really. That's just the one thing. So add child, let's change that. Add child. Okay, I need to create a new node. I can probably just do it in here. I need a state. So new state. New state. Let's get that. New state is equal to, how are we getting our new state? We're getting it by applying the action to our current state. Boom. And here's our action. And this gives us the new state. We are passing that new state in here, and we're passing our action, which we're just storing for reference. Excellent. Excellent. We now have our child added with its new state. And boop, 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 boop. We just returned a new. Oh, hold on. I guess we do need. Come back here. We are returning the new node. Okay, so I need add child to actually return the new. Oh, I already have the new node. Now I'm creating it in here. Okay, so let's just move that out then. Const new node. Boom. Add child, new node. Here we go, and then we return a new node. Sounds good. So that was easy. Could it be that easy? How can I test this? Let's see. I need to create a node. That's the only thing I need to test this, so let's do that. Let's do that in my little test area here. I already have a state, great. So, and I already have an action. That's all I need to really test this. Right, so if I were to do const node equals new node, new MCTS node, pass in the state, pass in the action, right on. Now let's take a look at what we've got in here. Doesn't show me? Doesn't show me? Okay. Here's my MCTS node. Here's my state as an int32 array. Here's my action as an int8 array. Here's my array of possible actions left to expand. Basically the entire board, or maybe not. Yeah, that's 0 because we're not. So let's make this the. No, okay, let's keep it like that. Actually, let's make it 2. Then there we go. Okay, no children, hasn't been visited. There's no reward. We haven't implemented any of that yet. So now I want to test the expand function, which I've got as a standalone right now. So easy to test. Oops. Right? Yeah, function expand. So let's do expand. Pass in my node. I'm not returning anything from expand. Yeah, I am. I'm returning the new node. Cool. So actually, let's get new node. Cool this. Co-expand is not what? Oh, okay. Take it easy. Take it easy. Don't need to see this anymore. I know it's fine. Let's take a look at our new node. State first. Let's take a look at that. Is that what we would expect? $512, yes, that's correct. Or is it? Hold on. Yeah, X is playing, so that's fine. Cool. Wait. 511, 512 would be. Why am I not sure about this? Okay. So let's just toString. Quokka is acting weird. Let me stop it and start it again. So index 2. Maybe I should have this here. It is kind of slow. Huh. Okay. Oh. So which one is it? 2048 or 512? Cannot read property 2 of undefined. Well, that's interesting. Oh yeah, of course, because I'm saying die. Ugh. Still though. What the heck? Now it's got this as 8192. I'm sure it was 512 before. Oh, that's some odd stuff. Alright, let's try this again. What? It keeps... Oh! Wait. What is going on here? Oh. What is going on is that... What is going on is that it's working. Because we are trying different... random different moves. That's why I'm seeing a different... Okay. Everything's under control. But I need to make sure that it corresponds to... Okay, so let's do that. This here, string, we're interested in the action there. And we want to take a look at our action to see if it corresponds to that. All right. So what do we got here? We basically have 0, 1, 2, 3, 4, 5, 6. This would be easier if I do it on the O player. Let's do that. Or actually, yeah, this is just gonna be, let's do this differently here. So we're gonna start off, X is gonna play in board 2, tile 1, which will should then make the next move play in board 1, and it's going to be player 0 that's going to be playing. That's what we should be getting here. Right. Well, not quite actually. Hold on. If I'm passing in a state here in action, this state is supposed to be the result of this action. Okay, so if it's the result of this action, we have played in board 2, we've played index 1, so this now should be a 1 here. Okay. And if it's the result, so it means player X has just played, so now I would have flipped that already. Alright, so that means that player 0 is to play. Okay. Now y is 2. Okay, yeah, this should now say we're supposed to play in index 1. Okay. So, index 2 is showing that indeed we had played 1, 2, 3, 4, 5. Yeah, okay, we're good. Now we want to check if we have made our move properly for player 0. Supposed to be playing in index 1, so we're in index 1. What is the move that you've made? So this is the random move that was selected, playing in board 1 and index 7. 0, 1, 2, 3, 4, 5, 6, 7. Cool. So that works. And what if it was the very beginning of the game? Let's say. Very, very beginning of the game. So all these would be set to 1s, let's say. Player X is to play. I don't know, we'll put it at 0. Oh, and that's interesting. Right, the root node action, there's no action that led to the root node. So it would be null in that case. Here, it doesn't really make a difference here for our purposes, but that's something to keep in mind. All right, it chose board 4 and index 1. The thing is, as soon as I change this, it's gonna, yeah. All right, whatever. But that's fine. So that works. It works. I would like to take a look, though, at... let's just make sure that our new node, that our node that children, oh, I can't see that because it's private. I'll see it that way though. Why? It's showing children as being empty though. That's because I didn't actually do add child. No, the add child is happening inside expand. So that should still work. Let's see, expand. Node.addChild new node. And in add child, we are indeed pushing. If it's private, I want this to be like that. So then why am I seeing this as empty? Oh, I'm not. Okay, cool. Here it is. It's just that this child doesn't have any children. I wasn't looking at the right thing. So cool. So this works. And it should also have reduced the, let's do narrower tests here. Let's just say we're supposed to move into index 1, board 1. It does that. It picks number 5 and removes it from the possible actions left to expand. Perfect. 2, 3, 4, boop, 6, 7, 8. Good. All right. I think this works for now, anyways. Let's just get rid of all, well, these for now. I have a feeling I might need this one again. All right. And here's the thing, right? Root node, I'm supposed to take in action. Let's take a look at this here. Create root node. I don't have much detail. With state as 0. So yeah, obviously no action. So this will simply pass in a null. I need to account for that in here, where read-only action is optional, which would fix my... Oh, not really, because I'm passing in null instead of undefined. Let's use, I mean, I specifically want it to be null. It's not just undefined. It's null. There is no action. I know there's not going to be an action later. It's null. That's it. Okay. It's fine. Doesn't affect any of the algorithms here, it would seem. Am I using that anywhere? I don't think I am. It's just for reference later. Oh, I'm using it here though. And saying, oh, it might be null. It's never going to be null because we're never going to be using find best child on the root node. Well, we're never going to be returning the that is not something that's ever going to happen. So there. Politely tell you to shut up. What is the significance of this again? I can't remember. Technical definition. I should take a second here. TypeScript. Ugh. It's not going to be that easy. Maybe if I do it that way. Maybe if I type in exclamation. Okay, there you go. When dereferencing a member. Oh! I never thought of using it that way. But yeah. Postfix expression operator may be used to assert that its operand is non-null and non-undefined. In contexts where the type checker is unable to conclude that fact. Specifically, the operator X produces a value of the type X with null and undefined excluded. Yeah, that's exactly what I'm doing. Okay, cool. Just wanted to make sure I was using this properly. Okay. So I think we're good here. What was I doing? I had finished my test here. And then I had just noticed that this, okay. So I think expand is good. We've got everything implemented in here. We just tested it. Okay, so now we go back up to our tree policy where we're returning a new node. Cool. Or we find the best child. All right. So find best child is supposed to return a node as well. But not a new node, a node that already exists amongst the children. of our node. And return v. Wait a second. Well, v is non-terminal. I think that might be a mistake. I think that might be a mistake. Oh no, we're just, okay, we're just, I see. We're just reusing v as a variable here. If v not fully expanded, and the reason we're doing that is, what is the reason we're doing that? So we're passing in a node. Obviously, the idea of the tree policy here is to return a new node, right? We're returning a new node. We're choosing a node to run our simulation on. That's what we're doing. So in our tree policy, is taking, well, v is non-terminal. So let's say we're beginning the game. Very first state. Everything's empty. Cool. So we create a new node with that empty state. Cool. While we're within computational budget, we first do the tree policy, passing in that new node with the empty state, returning a new node. And how is it returning that new node? Well, it's taking the node that we're giving it, checking if it's non-terminal, which it is non-terminal. It's checking whether it's fully expanded. It's not fully expanded. Good. Then it expands it. How does it expand it? It takes that node. It looks at all the untried actions, which is basically every possible action in the board, adds a new child using that action, applying it to the state. And then it returns v1. v1 returns here, which returns here. Boom. So now we've got a new child node with a new state. We then run a simulation on this here, which gives us a score, and we back up that score. Okay. So now I was just trying to figure out how come we are, if we're doing best child VCP, and we're assigning the best child to node and then returning, I wonder if that's why they're not using v1 here. And it's just v. I don't know. So from what I understand is we're just using this variable here and we're returning it. So I think I'm doing this properly. In any case, we're returning the next node. Oh, and we're doing it that way because if the node is terminal, if the node is indeed terminal, then we just return the node. Yeah. Okay. Okay, I think it makes sense. So now, let's see. Whoops. That's what I want. So I've got expand. I need to implement best child, and that's probably going to be a little harder than what I've been doing so far. This is where a lot of the math formulas and stuff for deciding which node, which child node we should be visiting next happens in this. That's where the UCT in the UCT search comes in. Upper confidence bound, UCB, whatever. Okay, yeah, I think UCT stands for upper confidence bound applied to trees, right? So it's the UCB1 algorithm, but applied to trees, something like that. Allergies. Whew. So here's our best child, and this is where you need to be understanding math notation, which I'm not great at. But I remember posting a lot of questions on Reddit about that stuff, so I might be able to track this stuff down and actually get inspired too by what I have done. My previous implementation of this should be illuminating. One moment, please. Okay. All right. Let's do this. So best child takes in V, a node, and C. That's this constant here, which I am just hard coding to 1.414, which seems to be the constant that works for this. Now, what the heck is all this again? Well, first, let's get in here. What are we doing here? We are argmax node of set children of V, right? So the node of all the children of the node that we're passing in that maximizes this function here is what we're supposed to return. So it means we need to iterate through all the nodes to choose which one maximizes this. Now Q, V, and V. So the Q here, let's see, it probably defines it somewhere. The node reward value, there you go, Q. So node reward value. Right here. Probably a better description right here. There you go. Oh, and this is where we get the 1.44, I think, because 1 divided by the square root of 2, 1 divided by the square root of 2 is, no, that's not it. Hold on. Square root of 2 is 1.44. So if we divide 1 divided by 1.414, no, that's not right. Oh, but that's when you're dealing with, rewards in the range of 0 and 1. Wait a minute. Well, whatever. I'm just going to go with 1.414 for now. because I know that's what I was using before, so I probably got that from somewhere. Anyways, let's look at our, there's our UCT. All right. X, the values of x, I, t, and thus xj are understood to be within 0 to 1. This holds true for both the UCB1 and UCT proofs. It is generally understood that nj equals 0 yields a UCT value of infinite. Oh, that's why. See, 2CP. It's because it's 0.7 something times 2, so it does come to 1.414. So let's see here, where n is the number of times the current parent node has been visited, nj, number of times child j has been visited, and cp is bigger than 0 as a constant. Yes. If more than one child node has the same maximal value, the tie is usually broken randomly. Values of x, y, I, t. What's I? What's t in here? I don't know. And thus of xj. Oh yes, of course. Thus of xj. The heck is I and t? I don't know. Are understood to be within 0. Okay. This holds true. What's that bar on top? I can't remember what that is. Is it like an average? Is it like, I don't know. It is generally, or the higher of, I don't know. It is generally understood that nj equals blah 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 blah. Okay, I think this. Okay. So yeah, number of times it has been. Okay, you know what? Let's look at my previous implementation. I went through all this, so let's try to build on that. Back propagate, expand, select best child. Best child. Okay, UCB1. All right, so I'm using a reduce here, which is smart, I guess. Or maybe not. This UCB1 run, so UCB1 is here. All right, so what are we doing here? We're taking our exploitation term. We're making, okay, so we're getting our exploitation term, which is the left part of this whole equation, if I remember correctly. This would be here. Exploitation, which is apparently, which is apparently simple matter of dividing the child dot reward, what we have stored and accumulated, and child dot visits. We're passing in the child here. Okay. And then our exploration term. What are we doing? Squaring the log of some child visit divided by child visit. Let's take a look, see if this makes sense with what we've got here. So QV, now we know Q is the reward, right? Yes, and N is the number of the number of times the child was visited. So that's what we're doing here. So that's our exploitation term. That's cool. Now we're dealing with our exploration term, which is this here. So the square root, that's what we've got here, the square root of 2ln is the log, right? So I think that's what we're doing, math log. Some child visit, right, of the parent node. Notice we don't have the little check here, little apostrophe or whatever. So the log, we're taking the log of some child's visit divided by child visits. Now, we're taking the log of all of that. Why is that? I think it's because we've got 2ln. It's the equivalent of just dropping the 2 and getting the log of the entire thing, I think. Let's pretend that that's what it is. I remember looking into this. Sorry, I think our algorithm here is sound. Now we're just we're taking the exploration, so the left side, and we're adding it to our exploration parameter, which is 1.414, and multiplying that by our exploration term. And that gives us a reward. That gives us a value. Does it? Or no? What does it? No, it just gives us something to evaluate. True, it just gives us something to evaluate the child compared to its siblings and select the best child. All right, so I think I can pretty much just copy this. And just rework it. But now there's one thing I was curious about though. What are we passing in as some child visits? Because according to our algorithm, some child visits is the... interesting. It should be the value of the parent, number of times the parent was visited. Oh, I know what I'm doing here. It's because I'm using a lookup table at some point and I'm switching nodes around to retain some of the values of, okay. So how do I get, let's see, how do I get the child to some child visits here? I'm passing that into run, and I'm calling run from where? I'm calling this from here, right? CDB run, some child visits. Some child visit is equal to what? That's right. I'm basically calculating this right here. So that's, it increases the computation a little bit, but I think it's worth it because it allows us to use a lookup table and basically have a state that we might have had somewhere else in the tree. Because obviously you can get to the same state in very different many ways, right? So it would kind of bite to have to not use the simulations that we would have done in this particular state. So for sure we're going to implement the lookup table. I'm pretty sure that's what I did in this implementation too. So if we want to do that, we can't just grab whatever the parent node has in terms of visits because that won't jive. Okay, I get it. All right, okay. Let's see. So let's passing a node. We've got all we need with the node because we've got the child nodes in there. We've got, okay. So let's see. We're going to do, what are we going to do? First we need to, well, we need a child. Find best child. So we're going to have to iterate through each child. The children array, in other words. Okay, so node dot children. Oh, I don't have access to that here, so let's make that. Was my MCTS node class, please? Thank you. Right here. So children won't be private then, I guess. We'll make it a, actually, no, I don't like that. Don't like that at all. I'm going to keep this a private. I'm just going to make a getter, get children, and I'm actually going to return a copy of that array. Yeah, seems safer to moi. Yeah. So get children is going to return, of course, an MCTS node array. And how's it going to do that? It's simply going to go return this. Actually, let's do that. There we go. Or even better practice would be to just return an iterator. And you do whatever you want with it, right? So I think that's what I'm going to do. So an iterator of iterable or iterator? Iterator of MCTS node. I like doing that. Then you can do, you want an array, do an array with it. Do whatever you want with it. Just, you know. That way it makes it really obvious that we're not just giving it the collection that we have stored in that class. So return this dot children, and I can just do values, I think, is the iterable. It's an iterable iterator, actually. Okay. That's cool. All right. So with that, I can now do node dot children. Cool. I know that it's an iterator, so if what I want is an array, all I have to do is this. All right. But I don't necessarily need an array. Do I need to keep track of I see what's going on here. This is like a this just returns the score. So this should be a separate function, really. Function UCB score, UCT, UCB score. That's just UCB1 score. I don't know what I'm going to need in here, but this just returns a number. Boom, boom. So obviously going to need child, which will be an MCTS node. We'll get to that in a second. Let's deal with this here first. So I'm going to need to run the UCB1 score on each of these children and figure out which one has the best score. So it means that I need to go through the entire thing. Let's see, how was I doing this? All right, so we're okay. Select node, right? So we're reducing PC return this UCB.run is bigger than this UCB.1.run. Okay, so basically, I see what I'm doing. Oh, but that's, wow. Not the most efficient though. Just realized. So, okay, so here's what I'm doing. I am running the UCB1 algorithm, the scoring for the previous element in the array, and I'm comparing it, so I'm running the same thing on the current element in the array. If it's bigger, then P stays P. If it's smaller, then P becomes C for the next iteration. Boom. But then we get to the next iteration, and we do the scoring on P again, but see where the problem is that we're computing the score for P every time, even though we just did that. We just computed it in the previous iteration. So there's some CPU cycles lost there. And since I'm trying to optimize, I'm not going to implement this that way. So how could I do this differently? Well, I could, instead of storing straight up P and C, I could use some kind of an object that stores the P here being a node, right? So I could store it, but also store their UCB score, which would make it so that I don't have to compute it every time. But in any case, I think that a reduce is not a bad way of going about this. Although might be more legible to do it imperatively in this case because it's quite complex. Like I'm looking at this, I'm not too happy with the code I wrote here. First of all, just using P and C. I know they're conventions, and this isn't really, it's a ternary, but it's not really obvious what's going on. Anyways, so let's not do a reduce. I think we're just going to do a straight up for loop. We're just going to use intermediate variables and do that. So let for const child of node.children, and we can do that because it's an iterator, or maybe not. Must have a symbol iterator that returns an iterator. Well now, hold on. Did I do this wrong? Oh yeah, I did. This should be an iterable, not an iterator. Well, in any case, it returns an iterable iterator. So let's do that. Iterable iterator. Now I think we're going to be fine. Yes, we are. Good. So I need to store, so let winner, or let's call it best child. How's that? Best child. Let best child equal, well, for now it's just going to type node, and it starts off with nothing really. That's what it starts off with. And now we assign, now we test. Oh, and here's the problem though by doing it that way, because I need access to the next one. Right. So I can't really do it that way. Now can I? Is there? Let's see. No dot children. Bummer. There's nothing I can do with this except next, but if I do that, then that screws the whole thing. So maybe we should turn it into an array. All right, so basically my two choices here are, well, I've got three really. I could use a for. If I turn this into an array, then I can use a simple for loop. I can use a reduce. I can use a for each, which I really don't want to do for that kind of stuff. So maybe I should go with the reduce, just make it better in terms of all right, let's see what this would look like. So we're taking in God's best child, we could do it that way, is equal to, let's take our node dot children, unpack this into an array. That allows me to use reduce. I used reduce. Now I've got access to, we're going to call this best child so far. And this is current child. Okay. Now the thing is, we need this to start with a particular type of object. Our object is going to be, and this is where, okay, this is going to be an empty object. That's fine, but we need to type it. So best child so far is going to be an object that has a score of type number, and let's call it, well, just node really. MCTS node. How's that? Oh, this is going to be some unreadable crap, but really, seeing all the binary stuff I've got all over the place, that's not going to be the worst thing. Best child so far is declared, but his value is never read. Yeah, we're about to fix that. We're about to fix that. So what do I need to do? I need to do get the best child so far. Dot score. now it's going to say that score is undefined, so I should add a score of 0, maybe? Maybe not. All right, let's worry about that in a second. Let's just implement this for now. So best child so far, that's score. If it's bigger than UCB1 score, this should be like compute, really. So compute UCB1 score, compute, okay. Compute UCB1 score. And this should be right. Pass in the node, really. We're going to need to pass in some other stuff, but we'll figure that out as we go. So this child so far is that score is bigger than the compute UCB1 node score. Actually, no, that's kind of silly because now kind of losing the score if I don't store it somewhere. So first, const current child score. Current child score is equal to compute UCB1 score. There we go, something like that. Then we check to see if it's bigger. If it is, so let's just use an if statement here instead of a ternary. What a ternary. So if it is, cool. Let's return an object. No, if it is, I just return best child so far. It's still the best child so far. But if it isn't, then in that case I need to return a new object that has a score of current child score and a node of current child. Yes, that would work, I think. Ah, crap. Really? Really? I need to do that? There's got to be a way. There's got to be a way to avoid this. If I do score 0 and actually let's just go minus infinity and then node, I don't know, undefined. It's going to complain about that, isn't it? Of course. Can I just do this? No. Can I? No. Yeah. Oh, look at that. Cool. That's kind of interesting. So that's one option. It is not obvious what is going on here. That's the one thing about the reduce that I don't like all that much, is this parameter that you pass into the callback here. That ends up, when you do, it ends up being the first element that it's using in the iteration of the array. It becomes your P, it becomes your accumulator, but it's really not obvious when you're not used to using reduce. So you're like, what is this here? What's going on? And It's kind of an initializer, if you will. I guess you could make a, for readability's sake, a separate variable called like reduce initializer, something like that, right? Boom, boom, and then do reduce initializer. Yeah. A little easier to understand for people that are not used to the reduce. But I mean, at that point, yeah. No, I think that's fine. Let's do that. Stores that, so return best child so far, nothing changes. Don't need to compute the score again, otherwise this becomes the best child so far. And once you're done with all that, you get a best child. Yay! A best child being, right now, this object. But we don't really care about the score. We just want the node, so I can do dot node. This is so common. Let's just do return best child dot node. There we go. That's better. So this would be our find best child algorithm. Now, seems to me like some child visits. Oh yeah, yeah. That's one thing I need to do. So what do I need to compute the UCB1 score here? I actually, let's see. So I pass in the child node. Don't I have access to reward? I've got them as privates right now. Do I want to mutate those things directly? Probably not. Probably not. Although this might save me a little bit of work. All right, well, for now, let's make them read-only since I need to read them. We'll worry about changing that if we ever need to do anything else to them. So, they're no longer privates. I can do that. Good. Now this exploration parameter, I can just hard code that in there. Don't even need it here, really. Although it makes for an easy place to change it. So I'll just pass it along then. So I'll pass that along as the exploitation parameter. There's a type number. And here we go. Exploitation param. Type number. Okay, I'm just being dumb here. This is the actual parameter. There we go. Okay. Now the only thing, so this is just going to be exploitation param, like that. The only thing we're missing here is some child visits. So let's put it here. Some child visits is also a number. Now, okay. So, well, that's not too complicated. I can just do a reduce on this one to get the sum. And I think that's what I was doing here. Yeah. Quite simple, really. Don't know why I needed 0. Oh. We'll see. Okay, so if I do that here, node dot children, right. So I'm using this twice. I don't want to make 2 arrays for, right. I don't really need to. I'm not mutating that array in a reduce at all. So let's do this then. Const children. Let's just call it children. Equals boom, boom, boom. Node dot children. There we go. And now I can simply do children.reduce. Children reduce, and here too, children reduce. Oh, I just thought of something. No, that wouldn't work. I do need that before. I was trying to figure out a way to just loop through it once, but I need the sum before we, yeah, okay. So children reduce, normally if we want a sum of something, we just start with P, but the thing is we need to extract it, so yeah, I know why we're doing it that way. So now I need like 2 initializers. This just becomes a little confusing. I'm just going to go back to having just that in here. We're going to have some child visits. And this should be children, right? Some children visits. Exploration, exploitation, it's exploration. Param, exploration, param, there we go. Uh-huh. Alright, now my objects is a little different, so I should be able to just grab visits straight there. Yes. And we're in business, except I don't like this PNC. Let's do let's call this sum, right? That's, well, accumulated sum. Accumulated. No, sum is fine. It's the sum so far, right? So sum. And this is current node. Current node. So current node dot visits. There we go. Actually, since we're iterating through a children, we could just call this child. Mm-hmm. Do I need current child, really? I don't think so. Let's just do child here, too. Child score. And this is just child score. Wait. When am I doing anything with this? Oh, that's wrong. This is child. Okay. And this is just child score. And this is just child. There we go. Child, some children visits. Exploitation param. So I think we've got everything we need here. It's what a big chunk, and there's probably stuff that doesn't work at all in here. It's my guess. So we're gonna have to do some testing. Where are we calling this? We're calling this in two places. We're calling this here. Now there is the question of, and I don't think I'm dealing with this at all in, or was anyways. That's interesting. When two children have the same UCB1 score, you're supposed to choose between the two at random. I'm not doing that in here. I am simply favoring whichever one was the biggest one. So the leftmost child, if they're both equal. Is that a big problem? Well, it introduces a little bit of a bias, I guess. But how often will they have? That's interesting, because like it might affect a little bit the algorithm. I don't think it affects it all that much. But in order to if we wanted to do that, we would need to check if it's equal. So that's an extra check that we need to do. Although it would only do it when it's not actually bigger. Might be worth implementing. Why not? It would make it fairer, more random, which is what it's supposed to be, right? So let's see, what would this look like if it's bigger? Then you return this. If it isn't, so let's do an else if they're equal. If they're equal. Actually, this is probably going to be quite rare. So this should be the third thing we're doing. So let's just else if. Oh, but that's the thing I wanted to avoid, though, where we are introducing an extra check. Whereas before we only had the one check. It was like, is it bigger? Boom. Then if it's not, this is what you do. Now I'm introducing an extra check, which will be done for at least half of the cases. Probably. Maybe not, but it's hard to weigh the benefit versus the cost here. I'm going to do it. This is the recommended way of doing it anyway, so let's do this. So if the best child so far dot score is smaller than child score, which is the second most likely situation. Well, they're both as likely, I guess, but then I just do this. Cool, cool, cool. Now, if what's going on here? Yeah, I'm just missing the. It's okay. Now, if it's not bigger, it's not smaller, then obviously it's equal. And if it is equal, we need to choose between the two randomly. So I can just do get random int inclusive. I want to choose between 0 and 1. And then I need another check here. So if get random inclusive is equal to 0, let's say. So if it's equal to 0, then let's actually, it's kind of silly for me to do this. I'm doing more computation than I need to. I can just use straight up math.random. If it's bigger than, what is it? It's from 0 to 0.99, right? So if it is from 0 inclusive to 0.99, then bigger or equal to 50 would be bigger or equal to 50 would be the halfway point, right? Would split it in two. Because we're 0 indexed, so 0 to 4.49 ends up being 50 elements, really. And then 0.5 to 99. Yeah, okay. So if it's bigger than that, then cool. Let's just return best child so far. Best child so far. But if it isn't, just return the other dude. Same thing here. Okay. There we go. Now, how do we test that? How do we test that? Let's go back down to our little test area. We're testing best child. Find best child. Find best child. We need to pass in a node. Oh, cool. We have a node. Let's do that. Although we need that node to be fully expanded, so how are we going to do that? We're going to do while. We're essentially going to do replicate what we're doing in here. While node is fully expanded. Yeah, okay. So while node dot is fully expanded. So while it is not fully expanded, keep expanding it. Node dot expand. No, actually it's a standalone. Expand node. Cool. So we're expanding node boop, 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 until it becomes fully expanded. At which point we can find the best child in that node. And how do we find the best child in that node? Crap. It's going to be impossible to really test this at this moment because we're not running simulations on them, so we don't have any. See, this is how this algorithm is so tightly intertwined. So let me bring this back up here just to clear this in my head. To run expand, we need. No, expand is fine. We're done with that. It's true policy we're worried about. Yeah. Where we are calling best child. Now, if, to call best child, we look at each node's visit and reward properties. But right now, they're zero. They're always zero because when we instantiate a new node, it hasn't been visited, it hasn't been rewarded, so it's 0, 0. The only place where it gets these properties set to something, incremented or set to a certain score or whatever, is in the default policy. So really there's no way to just really test the expand function. Well, I mean, we could set it ourselves. That's true. We could set those properties ourselves. It would be kind of weird because I don't know what to set them to. Like when and if I actually write a test suite for this, I'm going to be doing that, right? That's for sure. Not using this here for now. So then I could, all right, so let's do that then. To do test this function. For now, oh, and the funny thing too is that default policy probably also needs to, no, okay. We've got everything we need to implement default policy. Or do we? We're about to find out. So let's do that. Test this function once we have implemented default policy. So let's do default policy. Right on. How does that work? It takes in the state. Okay, interesting. So we're calling this from here, which is our UTC search. We're taking in the state of this new node here. Okay, new node.state, and then we run a simulation on that and return a reward. Cool, 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 cool. Mm-hmm. I actually need to also implement backup negamax. Once we have implemented default policy and backup negamax. Yeah, because backup negamax is the one that actually sets the reward in the visited. Okay. So default policy. Default policy takes in a state from the new node. Okay. What does it do with that? Takes in a state while the state is non-terminal. So we need a while loop. So while well, that's interesting because we've got a isTerminal function here, but it's tucked away under the node class. So let's extract this, since we're going to be using in two places. Oh, I can't. Not that easily anyways. Okay, so copy. Let's just get that in here. Function is state terminal, or state terminal term. State is terminal. State is terminal. Take in a state. Returns state is going to be of type state. Okay, and this is going to be returning a Boolean. Cool. Put that in there. If state. There we go. And then I can just call this. Might as well not have this in two places. State is terminal. Pass in dot this dot state. There we go. Okay. So now I can use this. I need to return this, of course. There we go. So now I can use this. So state is terminal. Pass in the state. Now we want to do while it's not terminal. So while it's not terminal, because we want to simulate until we get to the very end, until we're done with the game. Right? Now default. So while S is non-terminal, do choose an action uniformly at random from the list of actions possible in that state. All right, that's cool. I also have a function for that. So const possible actions left to expand. Wait, no, that's not right. Let's get back here. Choose an action at random from all actions possible for state S. Yes, okay. I think I get it. So we're just going to do, let's see. So if we call, all right, so we need an action. Our action, we're going to get it from get possible actions. So that's cool. This gives us an array. Now we want to choose one of those at random. That's cool. I've got a function for that already that I've called splice. What is it? Random splice, random array splice, splice random. Splice random. Now, of course, the fact that I'm splicing when I don't really need to adds some extra cost. Let's look at our utils here. Probably just use the random. Okay, let's do that then. Actually, that's kind of... yeah, okay, we'll save some. So let's do... Oh, but then I'm going to need to store this separately. Well, what's the cost, really? What are we... Well, splice is kind of a costly... It's not that bad because the array is going to be pretty short. All right, let's just do that ourselves. And I need to store the possible actions and possible actions. We're going to be here. I'm going to get that with this here. Get possible actions. Okay, now I get the index. So get random int inclusive 0. Then possible actions. Then our action is possible actions index. There we go. Okay. That seems to be the problem here. Get random int inclusive. Cannot find the... Really? There we go. So, while the state is not terminal, get the possible actions from the state we're in. Choose one. That becomes our action. What do we do next? We actually apply that action to the state. So, const. And we're mutating this, right? So the state now becomes a new state, essentially, that we are getting by applying the action to our state. So state and our chosen action gives us a new state. Boom, 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 until we get to a terminal state. Right? At one point, we hit our condition that, oh, we are at a terminal state. Game is done. Right on. Now we return the reward for state S. Now that's like that. It's just like return reward for state S. Yeah. Looks easy, but we need to figure out how we determine the reward and who gets it. How am I doing this in my current thing? Let's go to simulate would be what we're looking at. State.player. Wow, this state is terminal. Okay, so that's what I'm doing. Generate possible actions. That's what I'm doing. Then select an action at random. That's what I'm doing. That becomes our action file. That's pretty much exactly what I've just done. Now, apply action and then return this calculate reward. So I've got this as a separate function. And the calculate reward function is something that you would, something that you would pass in. Just give me the state, give me who the player is, and then calculate the reward. Yes, yes, yes. Now the question is, In my implementation here, I've got the player to play is embedded in the state, so that's cool. Because yeah, we need to be careful here. The reward, we're calculating the reward, so we're getting to a terminal state. As we're getting to a terminal state, we're going to be switching the player. We're doing that, right? If I look at apply action, first thing we do is flip the player flag. So even if like this, whatever action we've just made causes the game to be over, we're still flipping the player flag. Which I think is fine. That might end up turning, we can use that, I think. So really, once I get to a terminal state, if I look at the player flag, oh no, I see what I need to do here. I actually need to let's think about this. This is coming from so we got to think from the perspective, as we're scoring this, from the perspective of whoever we are running the simulation for, right? We want to get a score for them. So if they end up winning, we want this to be a 1. If they end up losing, we want this to be a -1, right? So reward, default policy, new node. So we're starting off with the root node. Right, it's my turn to play. I want to know, what should I do? The state reflects that it is my turn to play. Right. So now I return a new node. The new node has the action that I would have played and the next state. Now I take that and I simulate. So really, the player that is stored in the new node here, and the new node state, the player is not me. It is my opponent. It is my opponent. And I think that's why I had kind of implemented it before, where the player stored wasn't the player to play, but was the player that had just played. I think that's what my idea was. It prevented me from flipping, but it's not a big deal. I think I can do that. State, apply action. So I do need to store, and I think that's what I was doing here. I am storing the player, yeah. Which is kind of interesting that, let's see. Why would they not? I guess it's relevant to the overall algorithm. While state is non-terminal, do choose an action, play this, then reward for state. It's kind of interesting. How do you know, just with the games, the final game state, how do you determine that it's favorable for your player? But anyways, I think I know how to do this, so we're just going to store const player is equal to, let's see, I'm calling this from here. Okay, let's just apply action. I do need to check here if player is X. So let's extract that to its own function. And we're going to call it player is X. And then I can just, the thing is I wanted to, where did it extract it? Here. Bit 23, just so I know. Interesting, why does it say it's declared but its value is never read? Oh, because I've got an error here. And this is probably, yeah, because it's, okay. So, two choices. There's two places where I'm, three places. Yeah, no, I don't want to be doing that operation every time. So let's just, actually, this implies that it's returning a Boolean, right? When really it's not, it's returning a number. I could make it a Boolean, but let's call this returns 0 if player is 0, is O. Otherwise, player is X. So I should change this really to get bit 33. Test bit 33. 23. Test bit 23. Yeah, that's disgusting. Oh man. Test bit 23. There we go. We're going to do the same thing here. Oh boy, oh boy, oh boy. Okay, so const player equals test bit 23. Pass in the state. Now we're just gonna, if player is bigger than 0, player is X. If it's 0, player is, oh, there. Okay, so we've got that. Now how do we calculate the reward? Ugh. Well, we need to determine if we're winning. I have a way to do that, don't I? Has won. There we go. Oh no, wait. That's for the small board. No, which is fine. I can reuse that. I can reuse that. Where was I? There we go. So it's just like this better. Ay, ay, ay. What have I done? Okay. So I can do has won, pass in the state 9 for the entire board. I'm doing that somewhere else too. Oh yeah, I'm doing that in status terminal, basically. Return status terminal, and status terminal, I'm just checking to see if it's done. Oh, okay. So I guess it's an apply action that I'm doing that. Yes. Check if metagame is a draw. Check if metagame has been won and set appropriate bit. There we go. Why do I have that as player is X? Oh, because I'm emptying. Yeah, okay. So has won. Pass in the player. Cool. And now I get a Boolean. So if the player has won, if the player has won, okay, this is actually easier than I thought it would be. And that's thanks to bit boards and bit masks. If has won, then return a big fat 1. Yay. Else, let's check for, what's easier, checking for a draw? Well, that's the only thing I can check for. I can't check for a loss, really. So, well, I could check for, no. So let's check for a draw. Else if draw. So has, is draw, is draw, is draw. We don't care about the player because a draw is a draw. Okay, so state. Again, oh, and that's, nope. That's where, okay, so I should probably then check if metagame is a draw and set appropriate bit. So All right, let's extract this for God's sake. All of that. Extract to function in module scope that we're going to call meta game is draw. There we go. Good here. And that returns a boolean. Yes, yes, yes. So I can reuse that here. Where am I? Is if meta game is draw. Right? Pass in the state. Don't even need to worry about the index. Okay, and then I return a 0. Right? Otherwise, just return -1 because you lost. Now the question is, am I using the right player or passing in? Yeah, that's the thing, right? So I kind of need to flip the player. How do I flip the player? I can't really flip the player here. Ugh. That's a pain. That is a pain. The only other option that would make this easier would be to pass in from here. So store the player here, which would make sense, really. Yeah, this would make a lot more sense than trying to store it here. So how about we do that then? Let's get that. Okay, oops, let's grab all of this. Let's grab all of this. We're going to store a player straight in here. Like, who are we doing this for, right? We're doing this search for this guy. For this guy right here. Now, we just need to pass that into our default policy. We want to get the reward for the correct player. So let's get that in. And now let's modify our default policy to have a player, which is going to be a number. There we go. Now we can use that right there. And we are in the business. All right, so I think that's actually good. We're going to need to test this, but I'm out of time, so it's going to be a to-do for next session. Test this function. Here we go. Let's commit our changes. Like, what have we done? A bunch of stuff. I don't know. Implement. How about implement? We did expand. No, expand we had already done, right? Best child, right? Implement best child. Find best child. Best child and default policy. Default policy. Need to test both. Okay. Doop 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 doo. That's that. Push that up to GitHub. Come on. There we go. And we're done for today. Did I forget? No, 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 no. We're done. All right. Tomorrow.